So we'll continue our discussion on semiconductor laser diodes. And specifically we'll talk about noise today. So typically we'll think about lasers as sort of very nice sources of coherent light, right, with constant intensity and a nice sine wave at a well-defined frequency. But of course it's not perfect, right? And these noise mechanisms can affect the performance of a communication link as well. Okay, so let's look at. So there are two main types of noise in a laser. One is associated with intensity, known as relative intensity noise. Right? It's basically fluctuations in the intensity or the power coming out of the laser. And the other is phase noise, right? Which is jumps or fluctuations in the phase. So in this nice monochromatic output which is coming, the phase is sort of jumping or fluctuating randomly. So let's look at each one of them, starting with intensity noise. Okay, so it's called relative intensity noise or RIN for short. Okay, so if you look at, so let's say we bias the laser at some particular forward bias voltage and then supply a constant current, right? Then, like we saw this power current characteristics, so there should be a constant power coming out, right, corresponding to this input current. But if you measure the optical power as a function of time, okay, so the ideal case is, of course, that the power remains constant with time if the current is constant. But what actually you see is that there are some small fluctuations about this average value. Okay? So there's an average value here. Okay? This average value I can denote by some average power, right? So the average power, for example, I can calculate from the input current, right? That will be proportional to the input current, how much the input current exceeds the threshold current. But even though if we keep the input current constant, we see that there are some small fluctuations in the power. It's not exactly constant. Yeah. So you can see that, of course, this will limit my SNR, signal to noise ratio, right? So you can imagine, for example, when I make pulses. So let's say now I modulate the laser either through current or maybe through an external modulator. Then I'll make pulses in time. So now, instead of the pulses looking perfect, right, there is some noise here, right? And these are randomly fluctuating, right? So from bit to bit, like the noise level will vary. Of course, there will be some average and standard deviation, right? But you can see that, so there is some signal to noise ratio here now. So there is some noise level, and then there is some signal level. So this will limit my SNR, and ultimately, as you can see, like for example, bit error rates in my communication linkage. Right. So how do we characterize this noise? So you can imagine, let's say we measure this for some amount of time. Okay. So we'll get a trace, right? So which is the power as a function of time, right? So we have some data points here. So we can calculate the deviation, right? So the noise delta P, which is also a function of time, as basically the power at time t, and then subtract the average. So now if you take the average of the power, of course it's the average power, right? And by consequence, the average of this fluctuation, delta P, is 0, right? So, and then what we can do is compute what is known as the autocorrelation function of the noise. So basically what we do is take this trace and then shift it by some amount tau. Okay. So we compute this correlation function, okay, which is a function of some time delay tau, right? That is basically the average of this fluctuation in power, the time trace that we've taken, and then shifted by the same trace shifted by tau. Okay, so we have this trace, we shift it by tau, and then multiply the two and take the average, right? So by average, basically we mean like, so average here basically you take 1 over t. So let's say t is the time for which we measure, right? And then integrate over dt, whatever quantity we are taking the average of, right? We integrate that quantity over time for time capital T and just divide by capital T. So that's what we mean by average. Okay, so this correlation. So I do this for different shifts tau, right? So I'll build up this function c of tau, which is the autocorrelation function of the noise, and to basically see the spectral dependence of this noise. So you can imagine this is some time varying signal, right? And so it has composed of some frequency components. So what you can do is take the Fourier transform of this c of tau to find out what are the frequency components present here. Okay, so this is a general procedure that one does for any randomly varying signal in time. Okay, so any signal which is random, like noise, for example. So you know that for actual signals which are deterministic, right? So they follow some well-defined function with time. To know the spectral content, we just take the time domain signal and take the Fourier transform, right? But here, because this is randomly varying, right? So if I have some time t, I now again measure this for the next time t, the trace will not be exactly the same, right? Because it's randomly varying. So to characterize these randomly varying signals, what we do is take this autocorrelation function, right? And then find the spectral content by taking the Fourier transform of the autocorrelation. Okay, so okay, so in general, so let's say that's some function here. So if we take the Fourier transform, okay, so we get some function of frequency. So typically, for example, if you plot the c of tau, typically c of tau will be sharply peaked around tau equal to 0, and then fall away as you increase tau, right? Which is basically saying that so tau equal to 0 means I'm just multiplying the trace with itself without any shift, right? So when I multiply the trace with itself, you can see that all the negative, so there is fluctuation positive above the average, and then there's a negative fluctuation below the average, right? So when I multiply the trace with itself, then all the negatives also multiply together to give me a positive number. So this average will be, you can see, some non-zero high number. Right? And now when I shift it, what happens is like some positive fluctuations now overlapping with negative fluctuations, so that when I take the average, actually it goes, it falls away rapidly, right? And soon it goes to sort of zero. So this width of this correlation function is sort of giving me sort of the time scale over which the fluctuations are somewhat correlated, right? And after beyond this time, So if this is some tau c, basically, so fluctuations within a time tau c are sort of correlated with each other, but beyond tau c, sort of they're random. I cannot predict what the fluctuation will be beyond that. Right? And you can see that. So when I take the Fourier transform, so this noise spectral density here, right? So that will have some width, which will be so the width will be inversely proportional to the width in that. Okay, so if you have a more uncorrelated noise, so this is more narrow. So you might have heard of white noise, right? So totally uncorrelated noise is called white noise, where this is basically a delta function, which means the Fourier transform is flat. Right? So all frequencies are equally present. So that's white noise, and there is no correlation between the noise at different points. Okay. So yeah, so you can see that this is sort of the Fourier transform, right? So this is like right, and equivalently the correlation function I can write as the inverse Fourier transform of this noise spectral density. Okay, so now if I look at so tau equal to 0, right? The peak of my correlation function. So C at tau equal to 0. So that is from here you can see that's just the average of delta p square. Right? So from here that is just the integral of this power spectral density over frequency. Okay, so the peak value of this autocorrelation function at 0 time delay is basically the area under the curve of the noise spectral density. Right? I mean, this is like basic Fourier transform relations, which you already know. Okay, so the relative intensity noise in the laser, is defined as, so this relative intensity noise ring, okay, it's defined as the noise in a bandwidth of 1 hertz okay, divided by the square of the average power. Okay. So of course, so relative intensity noise, right? So intensity noise we calculate by taking the noise spectral density and then multiply by a bandwidth of 1 hertz, some normalized bandwidth here. And then relative comes because now we divide it by the DC power, square of the DC power. Okay. So this is also a function of frequency, this RIN, which is known as relative intensity noise. Okay. So I mean this B is just 1 hertz, so I mean that's just 1, right? So this is basically just this noise spectral density at frequency f divided by the average power square. Okay, and the units are so so this has units of watt square per hertz, right? Because you can see from here, right? So this has units of watt square. So this whole thing has units of watt square, and I'm integrating over frequency here. So this is watt square per hertz, and this is hertz. right? And in the denominator, I have watt square. So the watt square cancels out, and this is just per hertz. Okay, so the relative intensity noise uh, is typically measured in units of dB per hertz. Okay, so we take the dB, so we get a ratio of powers here square. So we just take 10 log 10 of that to get the dB, and then because I have a per hertz remaining, so I write it as dB per hertz. Okay, sometimes you might see this written as dBc per hertz. Sometimes a small c is put with a dB to denote. So this small c denotes carrier. Okay, so we have this noise spectrum here, and at zero frequency is the DC power, right? So this DC power, when you take the Fourier transform for DC, you know that you get so that's zero frequency, right? So you can imagine there's like a delta function peak here with magnitude uh, of the average power, right? And we are dividing by this average power, so which is like the carrier, right? And this noise is like a sideband to this carrier. So that's what this small c denotes here. So it's a dB relative to the carrier. Okay, so it's either dB per hertz or sometimes we'll say dBc per hertz. Okay, so basically this spectrum, this RIN spectrum. So you take any laser, and typically there'll be some RIN spectrum associated with that laser, which gives me the noise intensity noise associated with that laser as a function of frequency.
Sir,
Yeah.
it will be dBc per hertz or only dBc, sir? So because here you are multiplying one bandwidth, right, of 1 hertz.
Yeah, I mean, maybe I should not multiply by 1 hertz. It's sort of like it's just s by t square, right? I mean, you can think of this as the power in a 1 hertz bandwidth, right? But then the units, you're right, will be watt square if I multiply by 1 hertz. But yeah, maybe I should not. Okay, so let's say now I want to know the total noise, right? So you can see that for the light coming right out of the laser, the noise is distributed over some frequency range, right? And the total noise will be the integral of this over frequency, right? Just from here, right? So it's the same thing. You integrate this and multiply by the average power square, or you integrate just s. Okay, so finally, so what I'm interested in, right? So for example, let's say I put some data on this and then send it over fiber link, and at the photo detector, I'm detecting this light, right? And then what noise comes into my system or affects my system is the noise which carries over into my detection end, right? So the photocurrent coming out of my detector, that will have some imprint of this laser noise, right? And so that will depend on my photo detection bandwidth, right? So at the detector end, I have some detection bandwidth, so I'll basically see the noise within that bandwidth. Okay, so that's why the spectrum of this noise is important. So the total noise at the laser or at the transmitter end will be the integral over the entire frequency range, right, of this noise spectrum. But by the time I get to the detector end, then when I detect, only the noise within my detection bandwidth is important. Okay, so typically what this RIN spectrum looks like for these laser diodes. Okay, so here plotting the RIN. X-axis is frequency. Okay, so if you look at higher frequencies, it looks flat, like white noise. Okay, so frequency independent noise. Then you see a peak happening here at the relaxation oscillation frequency. So remember we discussed this frequency last time when we were studying the modulation of the laser diode. So this is some natural frequency at which the device responds due to the coupling of the dynamics between the carriers and the photons, right? So you can imagine that, and we saw that, for example, when we modulate, the response sort of peaks at FR. Similarly with the noise, right? So you can imagine there is some, let's say, any background noise which happens in the device. If it's close to this relaxation oscillation frequency, it's amplified, right? Because the system responds strongly at those frequencies. Okay, so you see a peak at the relaxation oscillation frequency. And recall this was typically like few gigahertz or something. Okay, and then sort of it goes down again, becomes flat again for some time or for some range of frequencies. And then it starts going up again towards low frequency. Okay. So typically, like once you get close to like megahertz range or below, then the noise starts increasing very sharply. Okay. And the levels we are talking about here, okay, typically, so this flat line level can go down to like minus 160 dB per hertz, right? Which means what? That this noise here is so 10 to the minus 16 times lower than the square of the DC power, right? Or in other words, like this fluctuation. So if there is some DC power here and then there is some fluctuation here, delta P. So this is like 10 to the minus 8 of the DC power. So that's, you can see, is really good. Okay. So the really best lasers that you can find nowadays have this sort of kind of noise floor. Okay, so this relaxation oscillation peak sort of goes up to like some minus 100 dB per hertz or something. And for low frequency, you can see it really goes up quite fast. Okay? So this is some low frequency noise which goes up typically as 1 by f or 1 by f square. Okay, and this is mostly like sort of technical noise coming from, let's say, some thermal expansion, some temperature fluctuations, which is giving me some thermal expansion of the cavity, some drifts in the current or the voltage source, or some slow drifts which are hard to compensate for. So there's a question, yeah, of course we want Rin to be as low as possible, right? So you can see that it's a direct measure of the noise, right? So if this is lower, then this fluctuation from the DC power is lower. And you can see that, so this spectrum you get for a particular average power, right? So if I increase so what you can sort of think of this noise spectrum is sort of characteristic of the device. And when I calculate relative intensity noise spectrum, I'm dividing by the average power, right? So one way to actually make my relative intensity noise lower, a straightforward way, is actually just work at high DC power, right? So if I increase my power, then this sort of comes down a little bit like that. Okay, so if this is at P1 and this is at P2, then this P2 is greater than P1. Right? So how do I go to higher power? Just bias it at a higher current, right? So It's P1 and P2, right? So if I go higher above threshold, then I go to higher power, and at higher powers, my ring spectrum is lower. So the relative intensity noise is low. And also this peak shifts slightly, because recall that this relaxation oscillation frequency also depended on the bias current. Right? So this actually depends on the bias current, something like this, right? Square root of. So if I go to a higher power by sending more current, then this peak also shifts. Okay, and then let's say I have some, so I send some pulses, modulate the laser, send some pulses, and then at the receiver end I'm detecting, right? So if the detector bandwidth is some B, then all the noise below the detector bandwidth, so if I integrate this curve below this B, that's the total noise, intensity noise I will see at the detector. Right? And typically, like your receiver bandwidths are set close to the bit rate. Right? So you have some bit rate, so you have some pulse duration in TB, and bit rate is 1 over TB. So typically, you set the receiver bandwidth just close to the bit rate. So basically, all the noise below that comes into your. Okay, so you can, yeah, so at the receiver you can see that, so you will get a signal which will be proportional, let's say, to this average, and then there will be a noise which is the integrated power below this, right? So if at the receiver I want to plot like an SNR, right, versus this average power that I'm sending from the transmitter, right? So let's say this SNR at receiver. So typically the SNR goes up with increasing transmitted power, right? Because what is, two things are happening, right? So by increasing the optical power, of course, my signal level increases. Also, you can see that the relative intensity noise goes down with increasing. Okay, so the SNR increases. Okay, so basically you can, so the signal power is sort of proportional to the average power, and the noise power is sort of, you integrate this or integrate the, yeah, so let's say integrate this over a bandwidth B, right? And then multiply by the average power, or in other words, sort of your SNR, which is the ratio of PS to PN, that is proportional to the, or inversely proportional to the area under this ring spectrum up to the bandwidth of detection B. Right. So if you go to higher power, then you can see that the area is going down because the curve shifts down. So the question is, what factors set this noise floor level here? Okay. So that's a good question. So the ultimate, so you can imagine that, let's say I somehow remove all the sources of noise. So I have a perfect current source going into my device. My temperature control is perfect. I take care of the defects, internal loss and scattering, everything. Okay, so then can this be pushed down lower and lower? There's an ultimate limit, okay, which is just given by quantum mechanics. Okay, so the ultimate level which these modern lasers, so if you're close to minus 160, that's pretty close to what is the quantum limit here, which is basically known as the short noise limit. So we'll discuss more about this noise, what this means when we study photo detectors and receivers. Okay, but this is basically coming from fundamental quantum mechanics. So basically, light that is, I mean, light is composed of photons, which are discrete particles, right? So when you have this light coming out of the laser, at the fundamental level, you are having these particles arriving, carrying packets of energy, like so each photon is carrying energy h nu, and these packets are randomly distributed in time. Okay. So, for example, if you measure the power with some photodetector and you look at the current, so basically you'll see this, right? You'll see some average power and then some fluctuations here. So even for a perfect source, so if you have a perfectly coherent source, even then you'll see some fluctuations here. Okay. And if you again do the same procedure, take the autocorrelation function. So the short noise is coming just due to the random arrival of photons. Okay. So basically the energy carried by the electromagnetic wave, light in this case, is not continuous, right? Which means, so let's say I put an attenuator in the middle and keep increasing the attenuation. Then at some point I'll see that I'm just getting one particle or one photon. So there's one photon which hits the detector, so I get a click. And then I wait for some time and then I get the next photon, another click, and then the next photon arrives. So, but I don't know when the next photon is arriving. Okay? It's not that all the photons are sort of distributed evenly in time. Not to go into too many details, but the photons follow what are known as Poissonian statistics, okay, which are basically just random statistics. So if you take some time interval and you try to measure how many photons will come in that interval, it has a Poisson kind of distribution, right? So I can't say for definitely how many photons are arriving. Okay? And so that is fundamentally coming from quantum mechanics, and that is the best you can do. Okay? So that level of noise is known as short noise. So this short refers to these individual particles. Okay, so I guess this kind of analysis was first done with like sort of bullet shots or something. So anytime you have discrete particles arriving randomly, you have this kind of noise distribution. So anyway, same true for photons. So that's what will give you the ultimate limit. And the modern laser diodes, especially for high frequencies, once you go beyond let's say a few gigahertz or 10 gigahertz or so, you're basically at the quantum limit. Yeah. So we'll see. I mean, we'll study this in a little bit more detail when we study photodetectors and receivers. Okay. Yeah. So that's as far as intensity noise is concerned. Right? So yeah. So for a good transmitter, you want as low a ring level as possible. Okay. And sort of the best lasers that you can get currently on the market go down to about minus 160 dB per hertz. Okay. So not only this level, of course, also what is important is how low can you go. So can you push this towards lower and lower frequencies before this starts shooting up? Okay, so then you will see also the area under the curve will go down. Okay, so that's intensity noise, right? Then the other noise mechanism in the laser is phase noise. Okay, so ultimately phase noise is what gives rise to a finite line width for the laser. Okay, so again, so imagine I am measuring the electric field of this optical wave coming out of the laser, right? Then for a perfectly coherent source, I expect that the electric field is a perfectly sinusoidal function, right? So the period here, is so 2 pi by omega naught, where omega naught is the frequency or angular frequency of the radiation, right? So yeah, so basically this extending to infinity is a perfect source whose spectrum is basically a perfect delta function, right? But of course, no laser is perfect like this. So what happens is that after some period of time, the phase sort of randomly jumps. So here, let's say it just jumps to this point. Okay. And then at some point later, it again, let's say, jumps. Okay, so we have these phase jumps happening every once in a while. Okay. So you can immediately see that. So if I have a waveform like this, right, not a perfect sine, but these jumps periodically, right? So now if I try to take the spectrum of this kind of waveform, it won't be delta function, right? Because it's not a continuous sine wave anymore, right? And you can immediately see that now we'll start seeing some finite widths. Okay, and again, without going into too many details, like sort of laser physics and the analysis of laser noise is like a big topic on its own. But for our purposes here, basically you can imagine that these jumps are happening randomly, right? So there is some time interval delta tau between these phase jumps, right? And that delta tau is distributed randomly. If you take some average of this time interval between the consecutive phase jumps, so there is some average time for which the phase is maintained, right? So this is known as the coherence time of the laser. Okay, and roughly you can imagine that this line width here, delta omega, is sort of 1 over the coherence time of the laser. Okay, so yeah, if you have phase jumping very fast, right? So if the time interval between consecutive phase jumps is very small, then you will see that the line width is broader, right? So that's a bad laser. A good laser is where the phase will be maintained for many cycles before there is a phase jump. right? Equivalently in the spectral domain, that would mean a very narrow line width. Okay, so and one way to think about where these phase jumps are coming from is basically spontaneous emission events. Okay, so we know that whenever stimulated emission is happening, so whenever the stimulated emission is happening, right? Basically, the field, the photon which comes out has the exact same frequency, momentum, and it's in phase with my incident photon, right? But randomly, if you have some spontaneously emitted photon, then it could have a different frequency, different direction of propagation, different phase. Okay, so when I add the field of this spontaneously emitted photon to the background field of the cavity, which is mainly determined by the stimulated emission photons, you'll see that the phase is different, right? So this phase jump you can imagine is happening because of the spontaneous emitted. Okay. Of course, it could also happen due to some other noise mechanisms in the laser cavity. But let's say again, somehow you eliminated all external sources of noise which can cause this kind of phase jump, then still you will have phase jump because of the spontaneous emission. Okay. So again, there's a whole complicated theory behind this without going into all of that. So the line width. So if I look at it in frequency, in hertz, the line width delta nu I can write as the spontaneous emission rate multiplied by this factor 1 plus beta sub c square. So this beta sub c, recall, was the line width enhancement factor. Right, so we saw this when we were studying the chirp imposed on a pulse generated from a directly modulated laser. Right, so you can see directly here. So the line width is scaling with the square of beta c, so that's why it's known as the line width enhancement factor. Okay, and photon is the number of photons in the cavity. Right, or proportional to basically the power coming out of the laser, right? And the spontaneous emission rate, recall, was something like this, right? 2 spontaneous emission events per photon lifetime in the cavity. Okay, and this beta c, recall, was typically between 2 and 8 for the semiconductor laser diodes. Okay, so recall we have also had an expression for this number of photons in the cavity when we were studying the DC characteristics of the laser. So, and basically it's also proportional, a fraction of the photons are coming out, right? So that's proportional to the power emitted from the laser, right? So I can also write this in terms of maybe more measurable quantities. Okay, so I'm writing the number of photons in the cavity in terms of the optical power coming out of the device. So of course I have a factor of h nu naught, which is the energy per photon, right? And then I have factors of this mirror loss rate, because so this was alpha mirror was depending on the facet reflectivities and the length of the cavity. This G threshold is the this gain coefficient at threshold, right? So this was equal to the total loss in the cavity, right? So because so this G threshold is basically equal to the total cavity loss, which is internal loss plus mirror loss, right? Also, yeah, right. And basically, this was also related to the photon lifetime in the cavity, like that. And Vg is basically the group velocity. Okay, so you can see that the line widths will be better at higher powers, right? Just like the intensity noise, the phase noise also gets better with increasing output power, right? Which is basically saying that so when you increase power, you are increasing the stimulated emission rate, right? So the fraction of spontaneous emission versus stimulated emission goes down, so the line widths goes down. Okay, so typically, for example, if you take the semiconductor laser diodes, plot the laser line width as a function of 1 over the optical power, right? So 1 over, so you should get a straight line, right? So typically that works well up to some particular power here. So this is decreasing 1 over p, so increasing p, right? So at until some maximum power, the line width goes down, and then actually starts increasing again due to some other factors. Okay, so beyond a very large output power, so right, so now I'm going like somewhere very beyond threshold, right? So let's say threshold is somewhere here, right? And I increase beyond this, beyond this, beyond this. At some point, like other factors start coming into the picture, and this doesn't even remain linear anymore. It starts sort of like saturating like that. So once this curve doesn't remain linear anymore, like this line width starts increasing again. But basically, if there is an optimum power or like maximum power up to which you can go, where you can get the minimum line width. Okay, so typically, like for example, if you take like any commercial DFB laser at telecom wavelength, this line width would be roughly like 5 megahertz. So if you just take a simple DFB laser, if you want to do better, you can go to more complicated designs like these multiple quantum weld lasers that I talked about. So there you can go down below like a megahertz. Okay, you can go to these external cavity diode lasers. There you can get to like 100 kilohertz. Okay. So you can get these range of lasers all the way from a few kilohertz line width, which is like sort of the best, but also the most expensive, to all the way up to like a few megahertz. So these are really cheap. DFB lasers are really cheap. And for most sort of telecommunication applications, you can see that this is still quite enough, right? So my line width megahertz, that's still almost like a delta function compared to, for example, my data rates, which are tens of gigahertz. But for certain coherent modulation techniques, like where you're encoding the phase, or these hybrid modulation schemes like QAM or things like that, you need the performance critically depends on the line. So there you want to go for these really low line lasers. Typically for a laser, the RIN and the phase noise or the line width go hand in hand. Okay, so for a laser, if you have if you take a laser with a narrow line width, its RIN typically will also be lower. Right? If you take another laser which has a higher line width, then typically the RIN will also be higher. So of course there are, I mean, even while writing these expressions, we make some approximations. And within the cavity, you can imagine actually intensity and phase noise are also coupled to each other. So things can get really complicated, but yeah. So typically these two things scale together. Typically, if you want a laser with a good RIN or a low RIN, you also want basically you want a laser with a narrow line. Okay, so this is still pretty good, right? So if I look at delta lambda, this is like 0.1 picometer at let's say 1.55 micron. Okay, so yeah, so again you can see, so you want a high power and other factors that you can control sort of, you want low loss for a narrow line width. Right? So if the losses are low, so G threshold is again like the total cavity loss. So if the losses are low, your line width is also low. Okay, so yeah, any questions on phase noise? So, I mean, of course, we skipped over some of the details, which we don't really need here, but if you're again interested in those kinds of details, probably you need to do some laser physics course. So again, like how you find out this kind of line width is you take this sort of autocorrelation function for this sine wave. Now you take phase jumps, right? So, so you'll have like e to the I phi t, and then you take like an autocorrelation with phi t minus tau, right? And then you model this phase jumps with some random process. And then you again take the Fourier transform and try to get some line width. Any questions? So with that, we come to the end of our discussion on lasers. So briefly now I'll just sort of mention, so as we saw that we could modulate our electrical data onto the optical wave by direct current modulation, but we saw that there are some limitations to it, right? So for example, we saw that speeds are limited to like 10 gigabits per second. You also get this chirp imposed on the pulse, which worsens the broadening on propagation in fiber. Okay, so for modern systems, basically we use what is known as external modulation. Okay, so basically we keep the laser on, right? So we just keep the laser running at a particular DC current. Right, so this is at some bias current here, it's just sending some laser, some IB constant current. So the power coming out is some constant value. Okay. And then we use what is known as external electro-optic modulator. And there we have our electrical data coming in. So this electro-optic modulator has a electrical or RF input, right, through which I send this electrical data, and it has an optical input where the laser comes in, right, and then at the output, the optical signal has now this data imprinted on it. Okay. So I'll just briefly discuss a couple of these electro-optic modulators which I used. Maybe you discussed these devices in some detail, maybe in your optical electronics course or maybe your photonic devices course, I don't know. But anyway, so you have to go for this external modulation once you want bit rates, let's say greater than 10 gigabit per second. So the modern, for example, if you take a DWDM system that is used currently, each channel, so each wavelength channel carries 40 gigabit per second. Right, so you can't do that with just directly modulating the current of the lasers, but you can get those speeds with these external electro-optic modulators. So there are two main types of these electro-optic modulators. One is known as electro-absorption modulator. Okay, and so this electro-absorption modulator is based on the same material system like indium phosphide or indium gallium phosphide that are used to make your laser sources. So one advantage of this type of modulator is that you can integrate the laser and the modulator on the same chip, right? So you have one same package device where basically the light coming out of that already has your electrical data. Okay, so basically how these devices look. So again, you have this sort of PN junction. Okay, so let's say I have, yeah, so here I have metal contact on the bottom. Okay, so let's say, so on this substrate here, I have my laser device sort of out of the board here. So the light is emitted by that laser and it's coming into this electro absorption modulator device. So this is my input light from the laser. Okay, so here again I have this PN junction kind of thing, maybe with an active region in between. So here basically this active region is what is known as an absorbing layer. So again, you could have like a single thin layer, or you could have like multiple extremely thin layers, few nanometer each, which would then be a multiple quantum well device. Okay, and basically what you do is you apply a reverse bias. So you can see that the laser structure is similar, right? And you apply a forward bias and you flow current through the device and you have light emitted. In this case, you apply a reverse bias. Okay. And basically, so if you look at the band gap of this absorbing region, that's so when no bias is applied, that absorbing region has a band gap smaller than the, so this frequency nu naught of the light. So this band gap here is smaller than the photon energy. Okay, so for let's say no voltage applied, V equals 0. So then basically the light is absorbed, you can see, right? And then now when I apply a reverse bias voltage, I set up an electric field across this region, right? And due to this electric field, basically what happens is that Okay, sorry, I had that other way around. So for no bias, actually the band gap is higher. Okay. So we have no absorption. And now when you apply voltage, basically the band gap goes down. Okay, and this is known as something called the Franz-Keldysh effect. Okay, so once you apply a high electric field across this region, this band gap actually lowers. Okay, and now it becomes lower than the photon energy. So now you have absorption. Okay, so now if you look at the power coming out of the other side, P out, right? So if I plot P out versus the voltage applied, so for 0 voltage applied, there is no absorption and all the power comes out the other side. So this is P in. But as I increase the voltage, right, this band gap starts lowering. At some point, it becomes lower than the photon energy. Okay, and basically now you absorb all the light. Okay, so now imagine, so now like if I have my electrical data and then I apply pulses of voltage V naught at the data rate I want, then I can then my optical power coming out will have high and low because of the absorption, right? So typically you can get this extinction between off and on, like easily like 15 dB or more, and the rate at which you can turn it on and off is you can go up to maybe 40 gigahertz or like gigabit per second. Okay. Yeah, and the main advantage of this is, as I said, like you can integrate this on the same chip as the laser. So there's a question of what is the advantage of using external modulation. So I just mentioned, right? So if you want to go to high data rates, right? Another reason is this chirp, right? So when I directly modulate the laser, we saw that we also impose a chirp on the pulse, right? Which can lead to even worse broadening due to dispersion in the fiber, right? So that will also ultimately limit the link lengths and the data rates you can operate at. With these external modulation, typically you don't impose any chirp. So nowadays, yeah, so if you're operating at those kinds of data rates, we exclusively do external modulation. Okay, so that's one type of modulator, which is known as the electro absorption modulator. The other type of modulator sometimes it's called electro-optic modulator. So that depends. That works on what is known as the Pockels effect, where basically, if I apply a voltage across the material, its refractive index changes. Okay, applied in proportion to the electric field applied. Okay. So, and if the refractive index changes, you know that. So, for example, if I have some length, so let's say I have some waveguide here, right, and some propagation length here. So, if I apply a voltage and have some electric field across this device over some length L, right? So, you know that the phase acquired here would be something like K naught N L. N is the refractive index of the device. So, when I apply voltage, this N changes. right? So then there is a phase change, which is k naught, which is 2 pi by lambda delta n. So there are many, there are a few materials which show this Pockels effect, and there are some details to which kind of material which show this effect. Not all materials can show this effect. For example, glass doesn't show this effect. So you need what are known as second order nonlinear materials or non-centrosymmetric materials. So basically the materials are a little bit more complicated. Okay. So one popular material is called lithium niobate, okay, or just LN for short. Okay, which shows this property. So so you can immediately see, for example, I could make a phase modulator straight away, right? So let's say I just have some length of this lithium niobate. I have light coming in, right? And then I have my RF port or the voltage source connected such that it applies voltage across the device. You can see that, right? There will be a phase. So if this, if there is a voltage which is a function of time, like my data, for example, then that will give me an electric field. So if this distance is d, then just v over d is the electric field, right? And then that gives me a index change, which is a function of time. So now you can see that I modulated the phase as a function of time, right? So you can make a phase modulator directly like this. You just have a section of this waveguide. So you have fiber, you have fiber coupled input and fiber coupled output, and inside the device you have this lithium niobate waveguide with electrodes on both sides, and you just apply. So you can see that phase modulator you can make straight away very easily, right? And then let's say I want to make an intensity modulator, right? So I want my output power or the intensity to vary like my data. Then basically what I do is make a Mach Zehnder interferometer out of this device. So I split my input into two arms. Right, so I have some metal contact electrode here, then electrode here, above and below, sort of the two waveguides. So let's say I split the power into half into the two arms, up and down, and then I apply again. So now, so let's say this is ground, and this here I'm applying my voltage. Right. So in this case, you can see that the electric field line is like this, whereas in this case, the electric field line is like this. Right. So from the perspective of the optical field, this electric field is pointing in the opposite direction. Right. So if the index change here is delta n, then here the index change will be minus delta n for the same applied voltage. Okay. So basically, you'll get a phase shift between these two arms. Right. So there will be a delta phase difference, delta phi between these two arms, which is basically 2 times k naught delta n f, where L is this length. Right? And this delta n will again be proportional to the voltage applied. So again, if the distance between these electrodes here is d, right, then this delta n will be something like n cube r EO, which is a constant of the device, times V over D. Okay, so this R sub EO is known as the electro-optic coefficient. Okay, so you can see it's a proportionality between the voltage and the refractive index. So higher this number, the more efficient the device is, right? So then here when you recombine, right? So this output power in the output port, so you add the fields, right? So there is a phase difference between the two fields. One is e to the I delta phi, where delta phi is given by this, right? So then, and when you so you add the fields and then take mod square for the power, right? So when you do this, you can see that this will go something as cosine square delta phi by 2 when you take mod square of this quantity. Okay, so delta phi is sometimes, or typically we write it as the applied voltage, right? Of course, it depends on the applied voltage here, divided by a constant which is known as V pi. So we write delta phi as pi times V over V pi. So you can see that when we apply voltage equal to V pi, we get a phase difference equal to pi between the two arms. Okay, so this V pi is a constant of the device, right? It depends on what material you're using. This distance is D and L, right? So this V pi depends on the device constants like that. Okay, so typically for a so intensity modulator made out of lithium niobate, typically you can get this V pi to be around 5 volts. Okay, so by applying a voltage of 5 volts, I can get a pi phase difference between the two arms. So I can go from constructive to destructive interference. So if I plot again here P out versus the phase difference delta phi or equivalently V, right? Then basically, so when I apply V pi, I go from constructive to destructive interference, and I go to zero output power from maximum output. Okay, so again now if my voltage is like a pulse trend depending on my electrical data, then you can see that my output power will now vary according to my okay, and the speeds now you can get to with these kind of devices is like up to 100 gigabit per second has been demonstrated, and there is no fundamental limit yet shown. Okay, so the speeds are limited by basically our parasitics of the device. So in principle, you could even go higher with these kind of devices. Okay. Yeah, so with these lithium niobate electro-optic modulators, you can get phase modulator, you can get intensity modulators, you can get even more complicated kinds of modulators, right? Because you can imagine that you can just have this device, you can split it into multiple paths and apply voltages at each of the paths, right? So you can get modulators specifically for the type of modulation you want to do, like QAM modulation, like you have IQ modulators. You have dual drive, push pull, like you can apply different voltages here. Okay, so all kinds of modulators with various versatile devices that you can use for different applications. You can make with these lithium niobate devices. Okay, so yeah, that's all I had to discuss for yeah, this external modulation. Any questions? Okay. In the few minutes remaining, maybe I'll just introduce the next topic, which is photodetectors or optical receivers. So now basically we are done with transmitters. And now we'll move on to receivers. The whole interferometer, yeah. So these waveguide paths that I've shown, all of that is lithium niobate. Right. So inside the device, the light is traveling in lithium niobate. So all this is lithium niobate. So the light is always traveling within the lithium niobate. And then you have metal contacts and electrodes at various points to apply voltages. Right. So basically, at the receiver end, what we want to do is we have some incoming light, right, which is carrying some signal as a function of time, and we want to convert it back to the electric domain, right? Because that's where we use the information. So basically, a photodetector is a device which detects light incident on it, and then generates what is known as a photocurrent. Right, which we can send across some load and measure maybe the voltage across that load. Right, so basically it will give me a current. So if this has some data imprinted on it, it will give me a current which is recovering that data. Right, so it's basically, you can see the opposite of the source, right? So for the optical source, we had we injected a current and then light was coming out. Here, light is coming in and it's generating. Okay, but since it's basically, you can see just the reverse operation, we can use the same materials that we use to make the lasers or the LEDs and just operate it in the opposite manner. So instead of forward bias, we operate it in reverse bias, right? So the same semiconductor materials, indium gallium arsenide phosphide, right? So we can use for photodetectors. And right, basically the things we are looking for is high sensitivity, which means I should get a measurable current for very low optical powers. Of course, I want a fast response, right? Which means that even for very high data rates here, this current should be able to follow that data rate. Of course, I want low noise, right? So up until now, we've seen that actually, apart from like this relative intensity noise at the laser source, there is no real noise mechanism affecting our signal, right? The signal is getting attenuated and dispersed as it's going into propagating through the fiber, but that's just sort of loss and distortion in the signal. There's no noise added on this, right? So apart from this noise which is generated at the laser source itself, the relative intensity noise, there is no other noise source. Now we'll see at the photodetector, basically we'll add noise to our signal. Okay? So we want photodetectors which add low noise, of course. Right. So here, when we recover data, we should be able to recover the bits properly. And of course, like compact size and again, like integration on a chip, and we should be able to easily plug a fiber and then detect the fiber mode. So all that again you can do with these materials grown on a chip. The same way we do for lasers. Okay, so basically this photocurrent, we want of course to be proportional to the incident power, right? And the proportionality constant is known as responsivity. Right, so you can see it has units of amps per watts. Input optical power is in watts, generated photocurrent is in amps. So this responsiveness is amp/watts. Right. So we want a photodetector with a high responsivity. Another quantity which is defined is called quantum efficiency. Okay. So this is the rate of generation of carriers, right? So basically, you incident photons and you're generating carriers here, which gives you the current. So the rate of generation of carriers divided by the photon incident rate, right? So the rate of generation of carriers, of course, is the current generated divided by the electronic charge. That's the number of carriers generated per second. The photon incidence rate is just the input power divided by the photon energy. And then I over P is, you can see, just the responsivity. Right? So the quantum efficiency is just related to the responsivity like that. Right, with the photon energy. Okay, so if I write the responsivity as the quantum efficiency times this electronic charge divided by the photon energy, right? So photon energy I can write as hc over lambda, and then there's this relation between the band gap, right? So again, I want the band gap of the material in my photodetector to be just smaller than the incident photon energy, right? So that this photon is absorbed. So this I can write as the wavelength in micron divided by 1.24. Right. So assuming that Eg is roughly equal to the photon energy, so that's hc by lambda. Right. So again, if I have E in electron volt, yeah, this relation of 1.24 by. Right. So you can see that the responsivity for a given quantum efficiency of the device scales with wavelength. Right. So does that mean that as I keep going to higher wavelengths, I just get better and better responsivity? Of course, that's not true, right? So what's happening is, as you increase the wavelength, your frequency is going down, which means your photon energy is going down, right? At some point, you'll become below the band gap, right? And then you won't absorb anymore. So in other words, this quantum efficiency will just drop to zero as soon as your wavelength exceeds the band gap, right? So typically, if you plot the responsivity versus wavelength, it looks like this. So it goes up to a certain point and this falls drastically. So the point at which it falls drastically, this cutoff wavelength is basically where hc by lambda c is equal to the band gap of my detector. Okay. So typically, we use indium gallium arsenide, where so this was like 0.45 and 0.55, I think, indium and gallium. So this lambda c comes out to be about 1.7 micron. Okay, so you can detect wavelengths below 1.7 micron. And you know, for telecom, we are basically interested in sort of like 1.3 to 1.6, somewhere in that. Okay, so basically the idea is this is basically a reverse bias p-n junction, right? So it's operating the opposite way as a source. So basically you have the same p-n junction, but now you just operate it in the reverse bias region. So you apply positive voltage to the n side. Okay. And now you have light incident into the material, okay, which generates photoelectricity.